Let's talk about angular momentum in a little more detail now. In general, angular momentum is the r vector, the cross product of the r vector and the momentum vector. And the way you can mathematically determine the cross product is by setting up what's called a determinant. You had determinants in math already a long time ago. Anyway, when you expand this determinant right here, okay, what you do is this is I, j, and k here are unit vectors along the x, y, and z axis. So to get the determinant, this is a 3 by 3 determinant. What you can do is you can multiply y and pz, that's y pz, subtract z and py, z times py. That would be the x component. Okay, so you multiply that by the unit vector along the x-axis. And then to get the y component of your determinant of your vector, you multiply this time z and px, okay, minus x and pz. All right. So that would be the y component of your angular momentum vector. So this is j hat. That's a unit vector along the y-axis. And finally, to get the z component of your angular momentum vector, you do xpy minus ypx, and then multiply that by the unit vector along the z-axis. So we can identify this as L sub x, the x component of your vector, angular momentum vector. You can identify this as L sub y, and we can identify this one as L sub z. All right. Now, in the particular case we're looking at here, we're restricting ourselves to a particle that's on the xy plane. Okay, so if it's on the xy plane, what's the value of z? Z is 0 on the xy plane, right? Therefore, if z is 0 on the xy plane, and what's the velocity, the momentum along the z-axis, the component of the momentum along the z-axis, p sub z. There's no motion, there's no vertical motion, right? So the component of the momentum along the z-axis is also 0. So z is 0, so this is 0. P sub z is 0, so that's 0. So this whole thing is 0. Okay? Z is 0 and pz is 0, so this thing is also 0. So you're just left with that. So we're saying that L sub x is 0. In fact, that's what we said. Your angular momentum vector is going to be perpendicular to your xy plane if your particle is moving on a circle on the xy plane. So L sub x and L sub y are 0. There's no x and y component for your angular momentum vector. Your entire angular momentum vector is pointing in the z direction. Okay? All right. So anyway, in terms of phi, L sub z is kind of simple. It's just the LZ operator. If you derive the quantum mechanical operator that corresponds to the z component of L, you just get h bar over I derivative with respect to phi. Okay? So that's your angular momentum operator, and so you can use that to determine the angular momentum values for your particle. So let's verify that if your particle is in a stationary state with quantum number m, it has a well-defined angular momentum. So here's your LZ operator. How do you verify if a particular property is well-defined? Then the state function, the wave function, must be an eigenfunction of that operator. So I apply LZ hat on psi. I should get back a constant times psi. Right? So do I get back a constant? Let's see what I get. What's LZ? H bar over I. Notice the similarity between this formula, this operator, and the linear momentum operator. What was the linear momentum operator? It's H bar over I d by dx. Okay. So this is the angular momentum operator, z component. So if I apply that on psi, and what's my psi? N e to the I m phi. What do I get? This is my psi. So it's going to be h bar over I. What's the derivative of n e to the I m phi with respect to phi? I can factor out the n. That gives me I m e to the I m phi. All right. So what do we have now? Let's simplify that. I over I will cancel. So what do you get? mh bar times n e to the I m phi. But what is this expression right here? That's just your psi. So what did we just show? We just showed that L sub z hat operating on psi gives you back a constant. And what's that constant? mh bar and times the original function, which is psi. So we say that psi is an eigenfunction of Lz. And so the z component of the angular momentum of your particle is well defined. It's equal to mh bar. Okay? So here's a quick follow-up question for that. What's the angular momentum if m equals 2? Lz is going to be equal to what? mh bar. So it's going to be 2h bar. All right? And that's just going to be your L also, because L is just Lz in this particular case, right? What's your L if m equals -2? It's -2h bar. So what do these vectors look like? So you're going to have, if this is your xy plane, the magnitude of this vector L right here is equal to 2h bar, okay? And k hat is the unit vector along the z-axis. The magnitude is 2h bar. So this is for m equals 2. What would it be for m equals -2? It's going to be pointing downward, right? Your L is -2h bar k hat being the unit vector along the z-axis. Okay, it's a negative, so it's pointing downwards, whereas +2h bar would be a vector pointing upward. So for this one on the left right here, what's the direction of motion of the particle? Follow your right-hand rule. Okay. Point your thumb to the direction of L. Which way are your 4 other fingers moving? Okay. Counterclockwise, right? So your particle is moving that way. All right. And if L is negative, which way is your particle moving? It's going to be clockwise. And the magnitude of the angular momentum is 2h bar in both cases. It's just that in one case it's pointing upward. So we're saying that if your particle is moving counterclockwise, then L is pointing upward. If your particle is moving clockwise, then the angular momentum vector L is pointing downwards. So that's how you interpret the direction of the L vector. The angular momentum vector is perpendicular to the plane of motion of your particle. Okay? And it tells you whether the particle is moving clockwise or counterclockwise on that plane. So, what if psi equals n cosine 2 phi? What's the average angular momentum vector? Well, what's this one? This is n times, again, you can see this is I, e to the I times 2 phi plus e to the negative I times 2 phi, right? Is this an eigenfunction of the LZ operator? Let's see, L sub z hat applied on psi would give you what? Let's plug this in for psi. Okay, there should be a 1/2 here, right? The whole thing is 1/2. Cosine 2 phi is 1/2 e to the I2 phi plus e to the negative I2 phi. So what do we get here? I'm going to get n times 1/2 times, what's LZ applied on e to the I2 phi? We've done this already. This is going to be 2h bar, right? M is 2 here. This is your M, and that's your M. M here is -2 because there's a negative there. So this is going to be 2h bar e to the I2 phi plus -2h bar e to the negative I2 phi. Is that an eigenfunction of LZ? Can I factor out a constant and get back the original function? I can't because there's a negative there. This is now going to end up being what? Well, actually, you could have just taken a derivative of this. You would have gotten sine, right? So you end up with n times 2 times sine 2 phi. So it's not an eigenfunction. So you say that LZ is not well defined. In fact, since it's a linear combination of two eigenfunctions that have well-defined LZ, what's the LZ that corresponds to this one? It's 2h bar, right? And the LZ that corresponds to this is -2h bar. And you look at your coefficient, it's the same. So there's a 50-50 chance that your angular momentum is 2h bar and a 50% probability that your angular momentum is -2h bar. So even though this, you can show that this is an eigenfunction of the Hamiltonian operator. It has a well-defined energy. What's the energy for this? M is 2, or -2. Energy for that is 4b, right? 2 squared b. That's an eigenfunction of the Hamiltonian operator. It's not an eigenfunction of the LZ operator. Okay? So what we're saying then is psi for m equals +2 and psi for m equals -2. They have the same energy, right? They are degenerate as far as the Hamiltonian operator is concerned, but they have different LZ values. Okay? So even though they have the same energy, they're degenerate. They're not describing the same quantum state. The quantum states have different, the two quantum states have different angular momentum values. One is positive, the other one's negative.